Okay, guys, I'm going to get rocking and rolling. Today we're going to go over 2.6, and then I'm trying to get this focus thing. Let's get going. So I'm going to go over 2.6, and then we'll get to 2.2. We're not going to finish 2.2, yet it is my favorite titled section in the book, More on Functions. Okay, so let's just get going. The 2.6 is on finding the domain of functions. Remember, the domain is where the x values exist, right? The domain is just where the x values exist. So if we looked at a basic graph, I mean, if we graph these, we know from last lecture, if I had something that looked like this, you would tell me, oh yeah, that domain just goes from 2 to infinity, right? And we wrote it like, actually we'd use a bracket for here, 2 to infinity. That was really in the last lecture. Well, in this one though, we're going to be given a function, an equation actually, and you're going to have to determine the domain. And in determining the domain, there's really two issues that could happen. The first we're going to go over is called restrictions on the domain. Restrictions happen from, or can happen, I should say, from having an x in the denominator. I'll give you a basic example. F of x equals, let's say, 2x plus 1 over x minus 5. Okay, if I gave you this function, for this section, for this part anyway, I'm going to ask you, well, what's the domain? Domain of f of x. And so we don't know the graph, right? I mean, you're more than welcome to try to graph it and figure it out, but we can get it directly from the equation. And it comes from the fact that in algebra, you can never divide by 0, okay? So you can never divide by 0, and because you can never divide by 0, this denominator can never, ever, ever be 0. And if it is 0, because of an x value, that x value is going to become a restriction. So let's see if this one has a restriction. I can kind of see that it does already. But the way we find it is we don't worry about the numerator. We just look at this denominator. And we're going to set it equal to 0. Really not equal to 0, I should say. So x minus 5 cannot be 0, right? If it was, if x minus 5 was 0, we'd have something divided by 0. And we call that undefined, right, in algebra. So we can't do that. So let's solve this out. We add the 5. And we wind up with x cannot be 5, right? Now what this means is that x can be anything its little heart desires, except it cannot be 5. So if we go back a few lectures ago, I kind of went over how to write this on the number line, but I'm going to review it real fast. So on a number line, if 5's here, and we've got 6 and dot, 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 eventually we get to infinity. And then 4, dot, 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 and we have negative infinity. If I wanted to write x can't be 5, what I'm saying is, look, x can be anything to the right of 5, and it can be anything to the left of 5, right? But remember, in college algebra, we're going to write this stuff in interval notation. So therefore, if I wanted to notate this in interval notation, it would be parentheses, negative infinity, all the way to 5, but I can't include 5, so it's going to be another parentheses. And remember, we use this union symbol because it means or. Jump over 5 and then go to infinity. So this would be our domain. Remember, the domain is where the x values exist. Well, the x values exist everywhere. They can exist from negative infinity or 5 to infinity, okay? Straightforward. So the first kind of issue, I call these red flags, okay? The first red flag is if we have an x in the denominator, it can cause a restriction on our domain. Okay, it can cause a restriction on our domain. Okay, I'm going to go on to another example of this. It kind of brings in stuff from the previous lectures. So let's say we've got one now that looks like this. G of x equals, let's say we've got 2x over x squared minus 16, okay? And same question, I'm asking you, look, what's the domain of g of x, okay? What's the domain of g of x? And we're going to solve it the same exact way. Look, I haven't gone over the other red flag yet, but I'm about to go over another one. But for now, we're going to stick to this one. Look, this red flag is still, hey, I've got an x down here in the denominator. It might cause a division of 0. So I need to solve it out. I do not worry about the numerator, okay? All I do is focus on this denominator, and I set it not equal to 0 and solve. So I'm going to say x squared minus 16 cannot be 0. And then I just solve it out. So I add the 16 to the other side. Then I take the square root. Remember, when you take a square root, you have to attach the plus or minus. So we get x cannot equal. So if I take, hold on, take the square root of both sides, I have to attach the plus or minus. So x cannot equal plus or minus 4, right? So now we've got 2 restrictions on this domain. So if I wanted to write this on the number line, just because I'm a visual person, we've got 3 intervals here, right? X can be anything to the left of -4. It can be anything in between -4 and +4. And it can be anything greater than 4, right? So if I'm going to write this how we write it in college algebra in interval notation, I'm going to say -∞ to -4. That's that first interval. Or the middle interval, -4 to 4, right? Or 4 to infinity. Okay? That would be my solution to the question of the domain of g of x. Well, the x can exist anywhere in this function except these 3. Let me kind of show you what I'm talking about, what happens. If I chose one of these restrictions, I'm going to choose +4. If I chose +4 and I plugged it into my function, we'd get 2 times 4 over 4 squared minus 16, right? 2 times 4 is 8. 16 minus 16 would give me 0. Hey, it would create a 0 in the denominator. And we can't have that. We can't have zeros in denominators. That leaves us with undefined. And so therefore, that's why our x value can't be 4. The same thing would happen with -4. I think the numerator would just be -8, but you'd still wind up with a 0 in the denominator. Because when you square a negative, that -4, you'd wind up with +16 still. Okay? So that's the first red flag on domains. The first red flag on domains is if we have x's in the denominator. They could cause restrictions on said denominator. The other restriction is if we have even roots. I should say red flag. The other red flag is if we have even roots. So let's say we had a function, let's say h of x is the square root of 2x minus 1. Why not? Now, I'm going to ask you the same question. What's the domain of h of x, right? Now, look, for this one, first off, for this red flag, it has to be an even root, okay? The even root, the fact it's a square root, we have an issue. If it was an odd root, we just wouldn't have an issue, okay? If it was a cube root, a 5th root, a 7th root, something like that, we're not going to have an issue. But because it's an even root, we have an issue. And the issue comes because domains are always real numbers, okay? The domain of a function only includes the real numbers from that function. We know with square roots, we could plug negatives under that radical, and we'd wind up with imaginary numbers, right? So we have to find out what x values keep us out of creating these imaginary numbers. Now, I'm just going to show you the way to do this. The way you do this is you put whatever's underneath that radical, 2x minus 1, and instead of saying it can't equal 0, what we're really about to say is that it can't be negative. And to say it can't be negative means it has to be greater than or equal to 0, okay? So if you're given a radical and you want to find the domain, I said even radical, I should say, even root radical, and I want to find the domain, I just stick whatever's underneath there greater than or equal to 0. So, and then I'm going to solve it out. So add the 1. I get 2x is greater than or equal to 1. Divide the 2. And I get x is greater than or equal to 1/2. Now, this is different than the last example, right? Remember, like if we go back to that first example, I wound up with x can't equal a number, right? So it can't equal one thing, it can be anything else, but it can't be one thing. This is different though. X can be a lot of things, actually, as long as it's greater than or equal to 1/2. So on the number line, now guys, I'm not going to draw number lines out after this, okay? So on the number line, we've got 1/2, and we got other numbers to the right and to the left. But our X value, now look, it's equal to, so it's going to be a closed circle. And it's greater than, so it's going to be to the right, okay? So therefore, in interval notation, this would be bracket 1/2 to infinity, okay? Look, I could plug any X value into here, and it would give me back a real number, okay? It would give me back a real number. I'll draw a function that kind of looks like this. Actually, if I drew this, I can draw this function for you, okay? It's not going to be perfect, but it'll be close. This function actually looks like this. It sits right here, and it goes forever that way, okay? And we can see that, look, if I gave you the graph of this function, it starts at 1/2, and it goes forever to the right, okay? So it lines up with what we found algebraically, okay? Questions? So guys, those are the 2 red flags, okay? And I'm going to, what's the word I'm trying to go for? I'm going to go over different examples with those 2 red flags, and what if we don't have the red flag? But if you have a question other than, man, I just need to see a few more examples of that, please let me know. Okay. Let's see here. So let's look at another example, and I'm going to pause this, and I want you to try it yourself, okay? See if you're getting it. If I gave you, I'm going to give you 2 examples. H of x equals, let's say, the square root of -x plus 4. We'll call that A. And B, we're going to say f of x equals x minus 1 over 2x plus 7. So I'm going to pause the recording right now. Guys, I worked that through and I forgot to unpause it. If you're watching this video later, you can kind of hit pause and see where how I did it on the page. My bad. Okay. Any questions from the class, though, on solving for the domain or finding the domain of a functional equation? Right? We did it on the graph last lecture. This is for the equation. Okay. I'm going to slowly go. Okay, I'm going to assume you're getting it. Okay, let's do a few more just to show you, well, what happens whenever we don't have an issue, okay? So let's say we had f of x equals, let's use some other weird, let's say z of x. Let's say we had z of x equals some nice, polynomial, like 2x squared minus 4x plus 1, okay? This is a nice quadratic equation. It's a nice smiling equation if you wanted to draw it. But I'm not worried about the graph. I'm worried about the equation here. Look, I don't have I don't have either of the 2 restrictions or red flags. I don't have a square root, right, at all. I don't have a radical at all. So I don't have to worry about imaginary numbers. That's out the window. I don't have an x in the denominator. You're more than welcome to write this all over 1. There's nothing wrong in that. But notice it's just a 1. It's a constant. It's not varying. So therefore, it's not going to change. There's no way we could have an x in the denominator here. So because we don't have either of the red flags, this domain, so if I asked you for the domain, would be all real numbers. Now, there's a few ways to say it. You can say all real numbers. And the book might say that. It might also use the math symbol for all real numbers, which looks like that. It's like a paragraph, but it's an R. The paragraph indentation in your composition class, but it's just an R. Or you can also say the interval notation, negative infinity to infinity, right? This means x can be anything on the real number line, from negative infinity to infinity. All 3 of these are fine. You'll see this one a little more in the book because the book and myself, we both stick to this interval notation. It's nice to kind of be consistent with that. Okay, so let's look at another one. Let's say we got h of x. equals, I'm not sure. I'm just going to make one up. Let's say we got 2x over x squared plus 9. And I know what you're thinking. You're thinking, Mr. Shirley, hey, that's got an x down there. It's got to have restrictions because it has an x down there. Well, let me show you what happens or how this happens when it looks like we have an x, but they're faking us out, okay? They're faking us out here. And let's see why. Okay, remember, I told you for domain, if I ask you for domain, the domain are all where the real numbers exist, right? So I'm going to solve this one like I said before. If we have an x in the denominator, I'm going to say x squared plus 9 cannot be 0, right? And then I'm going to solve it out. I subtract the 9. Hey, that's a big red flag. How in the world could I square a number and get a negative? Oh, the only way that can happen is in the imaginary world, okay? And I'm not worried if my x values are imaginary for restrictions because the domain is only in the real number line. So we'll see that happen, but I'll get there. So I'm going to take the square root of both sides, and I wind up with x cannot be plus or minus 3i, right? I wind up with imaginary because it's negative. We went over that in one of the last lectures. But look, x cannot be plus or minus 3i, and that's fine. I don't care if x is imaginary when it comes to restrictions. There's no way I could plug a real value for x in here and get back that undefined. And it has to do with the fact that we're squaring and then adding. Now think about this. I could never square a number and then add it to another number and wind up with 0, okay? Should say add it to a positive number. I could never square a number, which is always going to be positive, right? -2 turns to +4. -3 turns to +9, right? And then add it to 9, and then it wind up being 0. So it turns out, now look, if you go back to the example I did earlier with 2 solutions or 2 restrictions, I'm going to go back. Right here, you'll see this was a minus sign, right? And when it was a minus sign, when we moved it over, it became positive. Well, that's going to be 2 real numbers, right? 4 and -4 are 2 real numbers. This gave us 2 imaginary numbers. So therefore, my domain actually has no restrictions. It's all real numbers. Okay? My domain for this function is going to be all real numbers. Okay? Any questions? Any comments? Any concerns? Before we get rocking and roll. Okay, great. Guys, I'm going to stop here and give you the homework. So for this section, 2.6 is a little different. Actually, let me write on this one so I don't fill up another piece of paper. Section 2.6 is a little different. I'm going to give you some examples to do and homework to do. So on page 287, there's 3 examples I want you to try. They're from example 1 on page 287. And I want you to do A, B, and C, okay? What's nice about those, it works them through for you as well, but they're just 3 good examples of the domain. And then I want you to skip over to page 297, and I want you to do 1 through 8. And then I'm going to get a little picky and choosy here. 17 and 18. Actually, 17, 18, and then 21 through 24. I'm getting picky and choosy because your book kind of goes off the deep end in this section, and we don't have to worry about going off the deep end with the domain stuff. Okay? Any questions before I get on to section 2.2? Any questions at all? Awesome. Guys, you know what? Hold on. I'm going to pause this.